Have you ever seen a material do this when it gets heated? This is not an ordinary material. This is a shape memory material. It has the ability to remember a specific shape and change into that shape when heated. So how do these materials work? It is all based on phase transformations. You've probably seen phase transformations when water freezes. This is a transformation from liquid water to solid water. There is also a phase change when water boils. Here, the liquid water becomes water vapor. But what is the difference between the phases? The difference is how the individual water molecules are arranged. In liquid water, they are loosely packed together so they can move past one another. In ice, they are tightly packed together and they can't change places. But did you know there are actually multiple solid phases of ice? There's a hexagonal ice phase that is stable until negative 150 degrees Fahrenheit, and a cubic ice phase that is only stable below negative 150 degrees Fahrenheit. So how does this fit into shape memory materials? These materials also have multiple solid phases. There is a low temperature phase that is called martensite. But if we increase the temperature, the atomic alignment changes into another phase called austenite. So at low temperatures we have martensite, and at high temperatures we have austenite. How do we set the memory shape? To set the shape that we want, we must hold the material in the austenite phase at high temperatures. Here we have used screws to hold the wire in place on a metal plate, which we then put into the furnace to heat it. Inside the furnace, the wire transforms into austenite, which sets the memory shape. When we cool it down, it transforms into martensite, but it does so without changing the shape. In the graphic, you can see that the atoms have the martensite structure, but they align in a zigzag pattern so that the overall shape does not change. Now we can bend the wire however we like. The material does not change phase, but the alignment pattern changes slightly, so that they align in one direction. This results in a permanent shape change. Now if we heat up the wire, it goes through the phase change from martensite to austenite, and it returns back to its original shape. We can repeat this for almost any shape we want. Shape memory materials also exhibit another special property called superelasticity. Here's the same shape we saw before, and now we will pull it. But unlike before, this time the shape doesn't change, but it goes right back to its original shape. This is called superelasticity. This also works because of phase transformations. This material is a slightly different composition, so that at room temperature it is in the austenite phase. If we stress the material, we can force it into the martensite phase, and this will change the shape. But if we release the stress, it goes right back to the austenite phase and the original shape, because that is where it is stable at this temperature. You may have seen this before in eyeglasses that can be stretched without being permanently bent. We've shown you how the shape memory effect and superelasticity work based on phase transformations. This is an example of how material scientists study materials. They try to explain observed properties in terms of the internal structure. Then, once they understand the underlying principles, they can use them to make even better materials.